I'm Peter Kolb from Montana State University Extension Forestry and also Professor of Forest Ecology and Management.
Across this series, we will hopefully explain how climate and topography and tree species have interacted across the last 10,000 years across this ecosystem, and the role that humans have played in helping shape it. There are a couple of things that are really defining of northern Rockies forest ecosystems. One is that disturbance has always played a significant role in how these forests have evolved and how they function. And these disturbances are predominantly wildfire, but also the interaction of the original inhabitants of this region, the Salish and the Kootenai peoples, their role with fire, the interaction with wildlife, and weather patterns. Extreme snowstorms, ice storms, avalanches, all of these are natural processes that have helped shape these ecosystems. Today we often wonder, what is the role of modern humans and their management activities in these natural processes, this last best place that we often refer to, where we still have all of the original tree species and plant species, and many of these ecosystems still function the way that they did historically across the last 10,000 years. We'll examine what humans have done in the last 100 to 200 years since the industrial age. We'll look at modern forest management practices and the issues of climate change as they relate to the continued function of these systems and all of the inhabitants. Ecosystems are defined by the interaction of moisture and temperature across any particular landscape. Pictured here is the Northern Rockies ecosystem. What makes the Northern Rockies perhaps some of the most unique forested ecosystems in the world is the interaction of climate and topography. Typically, this region is influenced by four major weather patterns. Wet Pacific air coming across Oregon and Washington, the Cascades, and then colliding in a perpendicular fashion with the Northern Rockies ecosystems, which lifts them up and causes these air masses to drop significant amounts of moisture, typically in North Idaho and northwestern Montana. What also influences the Northern Rockies ecosystems are dry air masses coming across California and Nevada, hitting southern Idaho, and being influenced by the large valleys that heat up and create convection columns, thereby creating dry lightning storms in the summer, and sometimes allowing for some moisture to hit southern Idaho and southwestern Montana in the winter. But also significantly impacting the Northern Rockies are cold, very dry Arctic air masses that come directly from the North Pole and collide with the Rocky Mountains on the east side. These air masses have very little moisture but bring with them tremendous temperature changes and high wind speeds. These wind speeds can also fuel wildfires that are part of the Northern Rockies ecosystem. The eastern side of this mountain range also does get some moisture coming off the Gulf of Mexico, as air masses that come up across Louisiana, Colorado, and hit southern Montana by Yellowstone National Park. Historic measurements of climatic influences indicate that the eastern half of Yellowstone National Park is largely influenced by Gulf air masses, and the western half of Yellowstone National Park is largely influenced by air masses coming across Nevada and southern Idaho. As you can see, the Northern Rockies are really in a vortex of four different air masses that collide in this geographic area, creating turbulent weather patterns and unpredictable weather as well. This makes for the uniqueness of the vegetation that we have here and some of the historic interactions that have helped shape this ecosystem. If we start our examination of the Northern Rockies ecosystem in North Idaho and northwestern Montana, this is the area that gets the highest precipitation from the wet Pacific air masses. These mountain ranges are dominated by dense forests of multiple species, including water-loving grand fir, hemlock, and western red cedar. These are also areas that were influenced somewhat less by wildfires because typically they're too wet to burn, unless climatic changes brought on by normal climatic events create dry periods in which these systems tend to burn in large stand-replacing fires. If we take another look at the Northern Rockies ecosystems, we can actually draw a line across this mountain range where the Pacific air masses have their greatest influence, and therefore the most moisture and the highest growth rates and tree productivity occurs. To the left of this red line, we have ponderosa pine, Douglas fir, grand fir, subalpine fir, western red cedar, white pine, large lodgepole pine, and spruce as a pretty equal mixture, but with grand fir and western red cedar that require a lot of water dominating these landscapes. To the right of this red line, the Pacific air mass influence becomes less. And these landscapes are more dominated by the moisture that comes up across California and Nevada, hitting southern Idaho, as well as Gulf of Mexico moisture, and some infrequent snow from the Arctic air masses that come down. As a result, the lower precipitation levels exclude grand fir, cedar, and hemlock from these ecosystems, and these landscapes are dominated by ponderosa pine, Douglas fir, lodgepole pine, spruce, and at higher elevations, subalpine fir, all of which are adapted to grow on drier landscapes. These landscapes have been historically more dominated by fire events because on the average summer they're dry enough to burn. So if we look at the central Montana landscapes where more continental climatic influences play a larger role, forests are restricted at lower elevations by lack of moisture and at higher elevations than by cold temperatures. And so forests tend to become form a fringe or a belt on these mountain ranges and are much more interspersed and fragmented by grasslands and sagebrush prairies. Unique to the Northern Rockies are also the island mountain ranges of central Montana that are surrounded by low precipitation areas, short grass prairie. These include the Sweetgrass Hills, Bear Paw, along the Canadian border, south to the Highwood, Little Belt, Judith, Moccasin, Little Rockies, and Big Snowy Mountains. Aspect also plays a very important role across the Northern Rockies, where south-facing slopes get direct sunlight and radiation and heat up, whereas north and east-facing slopes only get indirect sunlight. What this results in is, even though both sides of these ridges get the same amount of precipitation, that in this case might be 20 inches, half of the rainfall and snowfall that hits the south aspects will evaporate off from the sun's energy, whereas the rain and snowfall on the north and east aspects will remain and soak into the soil, thereby allowing enough moisture to occur for trees to grow. This is shown by the wrinkles here, where the southwest facing slopes are pretty much a sagebrush grass with a little bit of juniper growing on it, whereas the north and east facing slopes will support Douglas fir, ponderosa pine, and lodgepole pine. Although less obvious on wetter forest types, the same phenomenon of moisture gradients caused by changes in aspect across mountain wrinkles occurs across all of the Northern Rockies. Here, western larch, that is less drought tolerant than the surrounding Douglas fir, turns color in the fall, showing its gold color and its preference for north and east facing slopes because there's more moisture there. Anywhere where larch occurs in the fall, you can see these moisture gradients pretty obviously. But if you were to go on these landscapes and measure them, you would see changes across these wrinkles on the mountains in species due to precipitation gradients. As a matter of fact, if we want to look at the entire Northern Rockies ecosystems, the impact of moisture and temperature create distinct and unique forest zones. Shown here on this slide is a hypothetical mountain range which represents the Northern Rockies running north and south. If we start on the driest, the ponderosa pine zone, this is where approximately 16 inches of rainfall allows trees to occur, and ponderosa pine is the most drought tolerant of all species, growing on the driest ecosystems because it has a deep taproot that can find water that other tree species can't. As we move from a 16-inch to perhaps 18 inches annual precipitation, Douglas fir, which is actually more drought tolerant than ponderosa pine because it can dry down more, starts to occur and is actually the largest forested zone across the Northern Rockies. Douglas fir can go from dry to wet sites, but pretty much these zones are defined by the occurrence or lack of occurrence of species. The ponderosa pine zone only supports ponderosa pine with juniper and limber pine, but since these are minor species, we call it the ponderosa pine zone. Where Douglas fir starts to occur is the start of the Douglas fir zone, and it can stretch all the way up into higher elevation zones where lodgepole pine is a dominant species. Higher in elevation, where you get steeper snowpacks, subalpine fir starts to occur. Shorter summers and deep snowpacks provide it with enough water to make a living, and subalpine fir is defined by its ability to handle really cold temperatures and to shed snow. Grand fir occurs at mid-elevations, and this would be typical of North Idaho, where perhaps 25 or more inches of rainfall occur each year. Grand fir is defined by its tremendous ability to regenerate in the shade. It has broad needles that allow it to collect sunlight even in shaded environments. And the wettest forest zone is the cedar hemlock, only occurring in valley bottoms across northwestern Montana, but actually as a broader species in northern Idaho, where deep ash soils retain moisture, and the collision of Pacific air masses with the northern Rockies drops as much as 40 inches of rainfall a year, allowing this water-loving species to grow. The driest forest zone, as mentioned, is the ponderosa pine. That growing here is typically a sparse forest, not a lot of tree growth because moisture is very limited, so the trees grow very slowly, with an understory of shortgrass species and sagebrush. Only ponderosa pine, juniper, and perhaps limber pine can grow in this zone. As more moisture occurs from the effects of the mountains on weather patterns, Douglas fir starts to appear. This forest can be pretty sparse. Growth rates are better than just the ponderosa pine zone, and it's basically, you know you're in it because Douglas fir is one of the species along with ponderosa pine. As we move to the higher elevation zones of Douglas fir, where also more precipitation occurs, lodgepole pine can start to occur. Lodgepole pine is unique in that it has serotinous cones that protect the seeds from fire. So these wetter, periodically dry forest zones of Douglas fir, within the Douglas fir zone, are characterized by fires that occur every 50 to 120 years. Because there is a significant time frame between fires, fuel accumulates, allowing these fires to reach greater severity, thereby killing trees, and that's why lodgepole pine has developed this unique characteristic of fire-resistant cones, and it makes its living by every 50 to 120 some years, or even 300 years, getting burned up by stand-replacing fires, and the protected seeds then recolonize lodgepole pine. Lodgepole pine can also grow into subalpine fir and grand fir zones if stand-replacing fires are a natural occurrence on these landscapes. As we move up higher in elevation, deep snowpacks, avalanches define the subalpine fir zone. As you can see on this slide, subalpine fir has this unique cone shape designed to shed snow. The dense canopy of subalpine fir also helps collect sunlight, which warms it up early in the spring and allows it to start photosynthesizing and becoming physiologically active before other tree species can do so. Moving down in elevation, where temperatures moderate but moisture remains high, we move into the grand fir zone. Grand fir now supports all of the previous species: ponderosa pine, Douglas fir, lodgepole pine, and additional fire-adapted species, western larch, survives in this zone, and it's really defined by being incredibly productive. More moisture allows trees to grow more, and these become light-limited environments where the trees compete for each other more for light than water. Grand fir, because of its tremendous shade tolerance, it grows in the understory, can create such complex structural characteristics as seen in this slide. And finally, the wettest zone, western red cedar zone, which gets anywhere from 30 to 60 inches of rainfall per year, now becomes truly a light-limited environment where the survival of tree species is determined by their ability to grow and regenerate in a shaded environment. As can be seen in this picture, competition for light is so fierce that not enough light makes it to the soil surface to allow for very dense understory growth. It's somewhat analogous to a cold temperature tropical rainforest in that aspect. The remarkable capacity of northern Rockies tree species and forests to recover are illustrated by this tenacious ponderosa pine seedling that's established next to this old stump, and these large diameter trees growing right out of the old railroad bed that existed here in order to transport the logs off of this mountainside.